Thank you for downloading this podcast from Talk Radio 702 and 567 Cape Talk. For more podcasts and more information on your number one news and talk station, please visit 702.co.za or capetalk.co.za.
Stand up for democracy. Find out about your rights as a voter. It starts with you. LeadSA.co.za. The Naked Scientist on Talk Radio 702 and 567 Cape Talk with Ridi Clubby.
I'll tell you what, lots of fantastic SMSs on the situation in Libya and Gaddafi, some of them hilarious, of course. I'm going to put them aside and then let's see if we can slot them in during the show sometime. But right now, we don't want to steal any more time off the Naked Scientist since we didn't have him last week and we suffered from withdrawal symptoms. Hi there, Chris.
Hello, I'm pleased to hear that, actually. I'd be rather worried if you said the opposite.
You know, I get the abuse when you're not available. It's very funny. The emails and the SMSs from our listeners are not, where's the Naked Scientist? When is he coming back? It's, what have you done with the Naked Scientist?
The sort of intrinsic assumption that you have done something to the Naked Scientist.
Yeah. Okay, without much ado, Chris, tell us about the heart being able to repair itself. How's that possible?
Well, 1 person in 3 over the course of their lifetime will develop a problem with their heart. It's the leading cause of morbidity, ill health and mortality, the reason people die. And the prevailing wisdom is that the human heart and hearts like ours in other mammals are very bad at repairing themselves. So if you injure them in some way, the most common way being having a heart attack, for example, when a coronary artery blocks up and an area of muscle is deprived of blood flow, and this leads to the death of that muscle. Well, after that happens, the muscle does not replace itself, and instead the heart heals up with a fibrous scar. You get connective tissue laid down, and instead of having a patch of heart that can beat and push blood around, instead you just get this fairly stiff bit of heart wall, which is all fibrous tissue. Or so we thought, because there's a paper which is published in the journal Science this week. It's by researchers at the University of Texas Southwestern Medical Center. The first author on this paper is Enzo Perello. And what they did was to say, well, mammals' hearts don't repair very well, but if you look at, say, fish and other simpler organisms, their hearts repair very well. In fact, you can chop out nearly a quarter of the ventricle, the main pumping chamber, of a fish heart, and it will completely regrow. Mm-hmm. And if you go into an embryo in a mammal, you can similarly chop out big chunks of the heart, and the embryonic heart can regrow. So at what stage does the embryonic mammalian heart stop being like a fish and start being like an adult? In other words, fail to regenerate. So they did this really intriguing set of experiments where they took 1-day-old mice and they cut away a chunk of the heart muscle, and then they followed up what happened. And they were really quite surprised to see that within 21 days, these hearts, from which they'd removed about 15% of the muscle at the apex, the tip of the heart, they had completely regenerated. They had completely normal anatomy. They had completely normal heart function. And they had no scarring to the heart. So it had completely repaired itself. And when they added labelling chemicals, which would flag up where the cells were coming from that were doing this repair, they found that it was heart muscle cells themselves in the animals' hearts which were dividing and multiplying and then migrating to the injured area to make good the damage. So then they said, well, that's rather strange because this does not happen in an adult, so at what stage does this turn off? So then they repeated the experiment with 7-day-old mice, and they behaved exactly like an adult. So something is happening between day 1 and day 7 of development, postnatally, which turns off this ability for the heart to regenerate. But this is very exciting because it says now we have a model system where you could study what's happening in these baby mice and ask what changes to make their heart stop repairing itself, both genetically, biochemically, physically and otherwise. And if you can work out what that sequence of events is, this shows that the heart can regenerate itself if given the right help. And therefore, if we could find a way of switching back on that pathway, fooling the mammalian adult heart into thinking it's a day-old mouse heart again, then we might be able to get it to repair itself rather than have the consequences of heart attacks or, as we have had so far, people doing studies on trying to put stem cells back into the heart from outside.
Sounds groundbreaking indeed. And then, Chris, what I want to know about is this new tool to improve the sensitivity of melanoma screening techniques. It's all optical biopsy?
Yes, and of course, melanoma is a serious problem, especially with pale-skinned individuals in very sunny countries. Australia, South Africa has big numbers when it comes to looking at how melanomas have increased. This is the leading cause of death of skin cancer, and these melanomas have gone up 100% in the last 10 years in vulnerable populations. And they're quite hard to diagnose. Often what happens is they get missed for a very long time, and even the experts are only about 85% good at spotting them. In other words, if you take a melanoma lesion on the skin and show it to someone who's their dermatologist, they'll only get it right and spot all of them 85% of the time. And even when you take a biopsy from a lesion, in other words, a skin sample, and you show it to a pathologist, then 14% of the time, studies have shown, pathologists disagree with each other about what the diagnosis might be. So clearly, this is leading to a lot of false positives, because doctors tend to be very cautious. They'll not want to make a mistake which could lead to someone developing a melanoma or dying from it, so they subscribe to the medical mantra, if in doubt, cut it out, which means that lots of people may be undergoing more severe or more radical therapies and surgeries and interventions than they really need.
Wow.
So is there a better way of doing the diagnosis? Well, there's a paper in the journal Science Translational Medicine this week. It's by Thomas Matthews, and he and his colleagues are at Duke University in America, and they have developed this really clever technique where they shine laser light of two different frequencies separated by a tiny time gap into the skin, into these melanoma lesions. And the first blast of laser light effectively suppresses the activity or the fluorescence, glowing, of melanin, the dark pigment in the skin. And the second burst of laser light then activates one form of that melanin and makes it visible. Because, believe it or not, there's not just one type of melanin. Melanin comes in two flavours. There's eumelanin, which is the dark stuff that makes skin a browny colour, and then there's pheomelanin, which is a reddier colour that forms freckles and things like that. And the ratio of these two different types of melanin is different in certain skin lesions. So if you have cancers and melanomas, they have more eumelanin, relatively speaking. And using this clever laser, what they call a pump probe technique, you can quantify how much of these two different colours or flavours of melanin are in a skin lesion, and this will give you a very sensitive readout of what the likely diagnosis is. And the good news is you don't have to take a biopsy to do this. They point out in their paper that the laser powers they are using could easily be adapted, so you could shine them onto the skin of a person to do what they're dubbing an optical biopsy. You wouldn't actually have to do anything invasive at all. You could shine the light in and record the light coming back out, and this would potentially enable you to work out what the diagnosis is without having to harm the patient at all.
Just a side question on that. Does the term diagnosis in situ mean what I think it means?
Well, the thing is that at the moment, the gold standard for doing diagnosis of pretty much any lesion is to take a bit of it away and give it to a pathologist to look at down a microscope. So they will take a piece of tissue, they fix it, so you make the tissue stable, you stain it with various colours which make the tissue disclose what its structure is, and then you look at it down a microscope, and certain diseases have very characteristic changes in the arrangement of cells and the features of those cells. This, unfortunately, though, is a slow process, and it's also a harmful process, because you've got to cut a piece out of a person. Well, if the person's got nothing wrong with them, cutting a chunk out of them is a bad thing to do, and it's against the Hippocratic Oath, which has always been do no harm. So much better if you can do something non-invasively, which is what this technique could in the long term enable us to do.
Thank you. All right, we're taking your calls, guys. Anything that you want to ask the Naked Scientist? I have a question from my colleague John Robbie. I'll ask it in just a moment. But first, let's go to Cliff in Randburg. Hi there, Cliff.
Hello, Rudy. Morning. I'd like to ask Chris, we all see nice trees, nice fruits, nice vegetables growing all over the place. Now, I've got a question. For instance, on a watermelon plant, the stem is so thin, and yet it pumps so much water into the watermelon that it gets so big and hard to lift it. I would like to know from Chris, how does that stem or how does that plant pump the water from the ground into the fruit?
Okay.
Hi, Cliff. Yes, it's using an active process, I think. See, plants have two ways of moving water around. One way is to rely on water evaporating from the leaves and the leaves are in connection with these very thin tubes, woody stem tubes, which go all the way from the leaf right down to the root, called xylem. And if you pull some water out of the top of the xylem, because water is a sticky molecule, then it pulls the water all the way up the plant, and that's passive movement. In a melon, though, you're concentrating all this water in one part of the plant. So how is that achieved? The likely way is to use the other way that plants move things around, which is their phloem. And phloem is a series of connected cells that move things actively. In other words, they use energy to pump. And the roots of plants have got lots of pumps that can move ions and salts around, and they can use this to draw water across cell membranes. And I think what the plants do is they pull water in, and then they actively move it to the melon, and then allow it to accumulate. And one way to do that is you make the melon have a lot of sugar in it, and the sugar helps to pull water into the melon flesh, because the sugar has an osmotic effect and draws the water in. I think that's the reason. But if anyone obviously is a plant scientist and can help us out here, I'd be very grateful for their input. But I will also check this so that we know we've got it right for next week.
We look forward to that. Thanks, Cliff. Adrian, stay on the line. I'm going to chat to you right after this.
The Naked Scientist on Talk Radio 702 and 567 Cape Talk with Reedy Clubby.
And of course, we're taking your calls. Adrian, thanks for your patience. Welcome.
Thank you, Reedy. Hello, Chris. I'd like to know, if I cut my hair on my head, obviously it grows back, and it will grow back and cut it again. But if I cut the hair on my arm, it will grow back to a certain length and stop there. Why would that happen?
Hi, Adrian. The thing that controls how long a hair grows for is because hairs on different patches of the body are following a different growth cycle, and this is determined genetically. So hairs come from hair follicles, and these are specialised collections of cells embedded in the skin which make the protein, because hair is a filament of the protein keratin, excuse me, and the hair grows during a phase of activity from the hair follicle called the anagen phase, and this lasts a variable length of time, and then the hair follicle goes into a breakdown phase, catagen phase, when the hair falls out, and then there's a resting phase called the telogen phase, and then it starts the anagen phase again. And by making hairs have different relative lengths of their anagen and catagen phases, you can adjust how long hairs will become on any bit of the body before they drop out. So a head hair grows for about 3 years or more before the follicles go into their catagen phase and make the hair fall out. So the hair can become quite long before it starts to fall out, or stops growing and then falls out. Whereas on other bits of the body, if you take an eyelash, for example, the growth phase, the anagen phase for an eyelash hair follicle is about 3 weeks. I think it's about the same for a pubic hair, 3 to 6 weeks. And so as a result, that limits the length overall that those hairs can get to. And that's a good thing, really, isn't it? Because otherwise it could get difficult seeing where you're going.
Okay, and speaking of hair, Kosi also has a hair-related question. Kosi in Bryanston, hi there.
Hi, I'd just like to find out what seems to me like a paradox. But I don't understand why, in terms of evolution, if you look at black people's hair, the texture of our hair is ideally suited for cold weather. And the texture of what you call Western European white people's hair is ideally suited for ventilation for the heat. So it seems a paradox to me that in Africa, where it's so hot, we should have this type of hair, and in Europe, where it's so cold, they should have that type of hair. And I compare that, for example, to sheep and goats.
Yeah.
Where you would say white people's hair is more the texture of goats, and you find goats where it's hot, and sheep where it's cold, and they can't survive where it's hot because of their coat. So I don't understand it seems to me like a paradox.
I love your question. So unique. Chris, what do you say to that?
Hello, Corsi. I also was intrigued by the very same question, and when I was at the Sci-Fest in Grahamstown 2 years ago, a lady was one of the guest lecturers from America, and her name was Nina Jablonski, if you want to look her up. And she works on this very question, and also skin colour, and how all the different colours of skins in different strains of humans around the world actually evolved in the first place. Fascinating lady. And I said to her, okay, so you've explained very well the skin colour, because humans evolved in Africa to start with, and evolved to have dark skin to stop ultraviolet light in the sun breaking down the folic acid in our body, and folic acid is needed to make healthy babies, because if you don't have enough folic acid, you have spina bifida. So I said, fine, I understand that. How do you explain the interesting hair quality that generally associates with being from Africa? And she said, aha, well, actually, this hair structure is very good at protecting the top of the head from incident sunlight coming from above. Because although it is thick and woolly, and therefore has or creates a good barrier between the top of the head and the air, which you'd think would be very insulating, and indeed it is, it's that very insulation that actually stops the top of the head getting too hot as well as getting too cold. So it actually serves both purposes. And although the hair is very, very dark, and you'd think, well, dark does absorb a lot of sunlight, this means the energy in the sun is dissipated into the hair rather than into the skin on the top of the head, and this helps to keep the head actually cooler and less likely to get damaged by sunlight.
Thank you very much, Kosi. I love these inquiring minds and observing the things around us. Very interesting. I wouldn't have thought of asking that kind of question. Thanks, Kos. Malcolm in Santon, hi.
Hi, Rudy. Hi, Chris. I've often flown on a small aircraft which...
Sorry, Malcolm, you're breaking so very terribly. I'm going to put you back on hold, and let's see if Mava can rescue that line while we take Jenny in 4 ways. Hi there, Jenny.
Hi, good morning. How are you?
Fine, thank you.
My question is, if you have an organ transplant, does the DNA of the transplanted organ change? Does your DNA change, or do they stay as they were?
Hello, Jenny.
Hi there.
Yeah, okay.
Well, the answer is that if you have certain types of transplant, then your DNA could change. I'm thinking if you have a bone marrow transplant, because you've had, say, a leukemia or something, and you take away a person's own bone marrow, and you then put in a new bone marrow from a donor person who is genetically matched to you, but obviously has healthy stem cells that won't give them leukemia, then if you test their blood group, it's possible when a person has a bone marrow transplant, you could detect a change in their blood group, because they're now making blood which is from the donor person. And that means that there are cells going around in their bloodstream which will have the DNA of the donor person, not the original person's DNA. And that means if they left a blood sample at a crime scene, then actually you could go looking and find two different genetic identities, potentially, because you could pick up DNA from the person who perpetrated the crime, plus you could pick up the DNA of their donor. The other possibility, the other thing to bear in mind, though, is if you have a solid organ transplant, so heart, a lung, a liver, or a kidney, then the reason you've had that transplant is usually because the organ is diseased. And by replacing the diseased organ with a new one from a donor, you are using their healthy tissue to do that important job in your body for you. And the cells that you have in your body from that person will have the DNA of them, of the donor person in them. And that will persist for the lifetime of that organ. It won't be replaced by cells from your own body, except in the instance of, say, where you make an anastomosis or a connection between, say, blood vessels, because the cells that line blood vessels, called endothelial cells, well, they will probably migrate back and forth between the two a little bit. But if you went back in 10 years' time and looked at the DNA in the donor organ, you'd find that it was the DNA of the donor, not the person's own DNA. And a good reason to think about why that would be is if you had cystic fibrosis, the lung condition, a transplanted lung will cure you of the lung problem related to cystic fibrosis. It could only do that if you've got a healthy copy of the cystic fibrosis gene, which you're going to get from your donor. And if you replaced all the DNA in the lungs with your own, then you'd be back to where you started, and that doesn't happen. So that's a good thing.
Thanks very much, Ginny. I have a question here from my colleague, John. He wants to know, what are solar flares? They have been in the news locally, and people are predicting they will cause havoc and may result in the end of the war, of the world. Do you know anything about that, solar flares?
Oh, I hope not. But the answer is that the sun goes through cycles of activity. And people have been studying the sun for a long time now. In fact, one of the most famous recordings of solar activity was by a guy called Richard Carrington, who in the 1850s was an amateur astronomer. He lived in the south of England, and he spotted this enormous sunspot, which was actually bigger than the Earth. And this is where the surface of the sun develops this cold spot. Actually, it's a cold spot. But it's where the sun's magnetic activity becomes concentrated in one place on the surface. And it's interesting because the sun is spinning like the Earth is, but it's not spinning at the same rate around the equator as it is at the top of the sun. So as a result, the sun sort of screws itself up like a spinning top and then unscrews itself. And it does this over a certain period. And when it does this unscrewing, it creates these interesting patterns of activity which become or culminate in sunspots, and you can get the ejection of huge chunks of charged plasma and electrically ionized material from the surface of the sun. And that's called a coronal mass ejection, because the corona is the material that surrounds the outside of the sun. And so you get this debris and material which is ejected from the surface of the sun at very high speeds and very high energies, say 1,000,000 miles an hour, and it will go streaming through space, and you get this big surge in charged particles, and if they hit anything in their path, then they're going to impart electrical charge and activity to the thing they impact on. And the Earth can occasionally be in the path of one of these coronal mass ejections, and most of the material will be deflected by the Earth's magnetic field. But if you have enough of it, as Richard Carrington reported in the 1850s, then some of it will begin to interact with things that are conducting on Earth. And in the 1850, what's now known as the Carrington Affair, or the Carrington Event, the sky went blood red because all these particles began to interact with the atmosphere of the planet. So the sky was red, the sailors reported the sea looking bright red, and wires on Earth began to conduct huge currents. So telegraph operators began to be electrocuted, and people got electric shocks and fires were started. The last time this happened, though not as severely, was in Quebec in Canada, about 15, 20 years ago, but nothing like as dramatically. And the sun goes through 11-year cycles of activity, and it's due to peak in the next year or two, when we should see a big surge in the numbers of sunspots and these coronal mass ejections. So hold on to your seats.
Thank you very much there, Chris. And to Malcolm, the line was so bad just a few minutes ago, so we don't have time for your question. I promise you, you'll be our first caller next week. I will personally make sure of it. Thank you very much,
I'll hold
Chris.
you to that, really.
Thanks, Chris. Chat to you next week.
Take care. Thanks, everyone. Bye-bye. Have a good week.
Bye-bye. And of course, all our features with The Naked Scientist are available as podcasts, and I can hear laughter and smiles all around.